Welcome back to Summarize Science. Ever wondered why robot hands in movies seem so capable, but in reality, they often struggle with simple tasks like spinning a pen? A big reason is the reality gap, the huge difference between how things work in a perfect computer simulation versus the messy, unpredictable real world. But now, researchers have developed a new system called DexNDM that dramatically closes this gap, allowing a single robot hand to expertly rotate an incredible variety of objects. Previous methods for teaching robots in hand manipulation were often brittle. They might work for a specific object, but would fail if you changed its shape, size, or even the orientation of the robot's wrist. The challenge lies in modeling the incredibly complex physics of contact and friction, which is where simulations often fall short. So, how did they solve this? Their approach has two main innovations. First, instead of trying to learn the physics of the entire hand and object system at once, which is incredibly difficult, they took a divide-and-conquer approach. They created a joint-wise dynamics model, which learns the unique physical behavior of each individual finger joint separately. This model predicts how a joint will move based only on its own recent history, effectively simplifying a massive problem into a series of smaller, manageable ones. But to learn about the real world, the robot needs real-world experience, and that's where their second brilliant idea comes in, the chaos box. Getting data is traditionally slow and requires constant human help to reset a dropped object. Instead of tedious, task-specific training, they simply put the robotic hand into a container full of soft balls and let it interact with them. This simple setup provides a massive amount of diverse, real-world data on contact dynamics, all collected autonomously without any risk of catastrophic failure. The result of combining these ideas is a single policy that shows unprecedented generality. Look at these examples again. The robot can handle objects with high aspect ratios, like this long bar, and even small or irregularly shaped objects, all with different wrist orientations. When compared to previous state-of-the-art methods, DexNDM consistently performs better. Table 2 here shows it substantially outperforms a method called AnyRotate on its own test objects. And when compared to another system, Visual Dexterity, it achieves comparable or superior results, while also being able to handle a much wider range of object types. This isn't just a research demonstration, it has practical applications. The researchers used their rotation policy to build a teleoperation system where a person wearing a VR headset can guide the hand to perform complex tasks, like assembling furniture or using tools, with a new level of dexterity. So, to recap the key breakthroughs, first, they simplified the learning problem by focusing on the dynamics of each finger joint individually. Second, they developed a clever, low-cost, and fully autonomous way to collect real-world data using a chaos box. This combination allowed them to train a single, highly generalized robot brain that can adapt from simulation to reality and manipulate a huge variety of objects. What does this mean for the future? This breakthrough could be a major step towards creating truly general-purpose robots. Imagine robots in manufacturing, logistics, or even homes, capable of handling any object they encounter with human-like dexterity. The reality gap is still a challenge, but this work shows we are getting much, much closer to bridging it. Thanks for watching Summarize Science.